Right now, sitting in your pocket or, maybe resting on the desk right next to you is what is essentially a pressurized chemical cauldron.
Yeah, that is a highly accurate way to put it, actually.
Right. Because you probably think of the lithium-ion battery in your phone or your electric vehicle as this solid, stable block of technology, just a quiet little brick.
But internally, it is a highly active, constantly reacting environment.
Exactly. And the crazy thing is, if the internal temperature of that battery hits just 135 degrees Celsius, which frankly really isn't that hot in the grand scheme of a car engine or a device left in the sun, the microscopic plastic guardrails inside it will literally melt.
They just dissolve, yeah.
The chemicals will mix, and within 60 seconds, that little black rectangle can generate a literal jet flame, spiking to over 800 degrees.
It's terrifying. And, this isn't some rare manufacturing defect we're talking about. It is the underlying physical reality of the liquid lithium-ion batteries that power, well, pretty much every single aspect of our modern world.
Welcome to the deep dive. Today, we are exploring a silent revolution that is going to fundamentally change how you interact with your technology.
And it's something the industry doesn't really like to advertise loudly,
Yeah.
but we have spent the last 3 decades essentially trying to tame a controlled chemical fire.
Yeah.
We haven't solved the volatility. We've built better armor around it.
Right, until now. Because today we are talking about the massive leap from those volatile liquid batteries to all solid-state batteries. Today is March 25, 2026. And after years of what the tech world cynically called empty promises, this technology is finally crossing the threshold.
It's moving from laboratory theory right into your actual reality.
And to really unpack this, we've pulled together an incredible stack of sources. We're looking at academic journals like MDPI, massive industry reports from GASCU and Bloomberg NEF, and direct data from companies like QuantumScape.
Yeah, the mission today is to dig into the actual technical breakthroughs, the commercial timelines, and just the cold, hard scientific facts surrounding this transition.
And to set the stage for this, we have to recognize a hard truth, right? We have officially hit what engineers call the electrochemical ceiling.
Right. Squeezing more power out of our current liquid batteries is no longer just, difficult. It is a physical impossibility without fundamentally compromising your safety.
Wow.
Moving to solid state is no longer a luxury upgrade. It is a strict necessity for the future of transportation and the energy grid.
Okay, let's unpack this. Because before we get into the bleeding edge scientific breakthroughs from 2025 and 2026, that exactly why we are so desperate to ditch the liquid in the first place.
Yeah, we have to look at the baseline.
Right, like how does the battery sitting in my driveway actually work right now?
Well, it all comes down to internal architecture. Inside a traditional lithium-ion battery, you have a negative side, the anode, and a positive side, the cathode. And separating them is a liquid organic solvent. We call this liquid-electrolyte. So when you charge your phone or you step on the accelerator of your EV, lithium ions are physically traveling back and forth through this liquid pool between the two sides.
I always like to visualize this as like a high-speed, sloshing liquid highway. The lithium ions are the cars commuting back and forth between the two cities.
That's a great way to picture it.
And because you obviously cannot let the opposing lanes of traffic crash into each other, you have a physical piece of porous plastic, the separator, acting as the guardrails.
That analogy works perfectly because it highlights the major vulnerability. The fundamental bottleneck we've hit is the liquid organic solvent itself.
Because it's flammable.
It is incredibly flammable. If your battery gets physically damaged in a car crash, or if a software glitch overcharges it, or it simply gets too hot, the liquid starts to break down and release gases.
Which creates pressure inside that sealed little box.
Exactly. It creates immense pressure, and it leads to a chain reaction called thermal runaway. And this can start at temperatures as shockingly low as 80 to 120 degrees Celsius.
Which means the battery is literally cooking itself from the inside out.
Yeah, the heat rises exponentially. And once it hits that 135 to 165 degrees Celsius mark, your plastic guardrails, that separator, it just melts and collapses.
Oh, man.
So the anode and the cathode make direct physical contact.
And when the guardrails vanish on a high-speed highway, you get a catastrophic pileup.
A massive internal short circuit. All the energy stored in the battery releases at once. You get toxic gas venting and
Those literal jet flames we mentioned earlier.
exactly jet flames.
So, okay, if the liquid is the problem, my immediate thought is, well, why didn't we just swap out the flammable liquid for a non-flammable liquid like 10 years ago. Why go through the massive headache of inventing an entirely new solid architecture?
You're touching on years of failed experiments right there. I mean,
Hmm.
chemists tried that
Yeah.
constantly. But every time they found a liquid that wouldn't catch fire, it was either too sick for the ions to swim through, or it reacted poorly with the metals in the battery, which degraded the capacity.
I see.
You need a medium that conducts ions perfectly but doesn't conduct electricity. And those highly flammable organic solvents were literally the only things that offered the right balance of performance.
And the reason this sealing is becoming a crisis right now, according to our sources, is because we are demanding way more from our batteries.
Right.
Like to get an electric vehicle to drive further on a single charge, engineers desperately want to use a pure lithium metal anode, right?
That is the holy grail of battery chemistry.
Hmm.
Traditional batteries, the ones we use today, they use graphite for the anode. And graphite works fine, but it's bulky.
It takes up space.
Exactly.
Hmm.
A pure lithium metal anode has a massive theoretical capacity. We're talking 3,860 milliamp hours per gram, which is roughly 10 times the capacity of graphite. It's the difference between a thimble of water and a bucket.
That's a huge jump.
It is. But here is the fatal physical flaw. When you use pure lithium metal inside a liquid electrolyte, the lithium doesn't plate smoothly when you recharge it.
Right. The sources dive really deep into this. It forms these microscopic, needle-like crystalline structures called dendrites.
Yes, dendrites.
I sort of picture them like stalagmites growing on the floor of a cave, but they grow rapidly every single time you plug your car in.
That's the exact mechanism.
Hmm.
And because they are sharp and they're growing through a liquid, there is zero physical resistance to stop them.
So they just keep growing.
Right. These dendrite spears grow straight across the liquid highway, they pierce right through the plastic separator, and they cause that catastrophic short circuit we just talked about.
So automakers are completely stuck. They
Yeah.
want to use the pure lithium metal to give you, a 1,000-kilometer range. But
Yeah.
if they do, the battery grows spears and explodes.
Yeah, it's a non-starter.
So instead, they stick with the weaker graphite. And then they have to surround the entire liquid battery pack with heavy, expensive active cooling systems.
You have armored casings, firewalls, all of it.
Yeah.
You end up spending so much vehicle weight and physical space just trying to prevent a fire that you severely limit the actual energy payload of the car.
Which brings us to the grand promise of the all-solid-state battery. If you replace that flammable liquid pool with a solid, inert block of material, you theoretically solve everything at once.
Everything.
You strip away the heavy cooling systems, you physically block the dendrite spears from growing because they can't pierce a solid rock.
Right.
And you can finally use that ultra-powerful lithium metal anode.
That has been the theory for decades.
Yeah.
But taking the liquid out introduced a massive, seemingly impossible mechanical problem. Engineers call it solid interface impedance.
Okay, here's where the physics gets really tricky. Our sources use a great analogy for this. Moving ions through a liquid electrolyte is like swimming in a pool. The water effortlessly conforms to your body, so you just glide right through. But forcing ions to move through a dense, solid ceramic or sulfide material, it's like being pulled out of the pool and trying to run a sprint through a sandbox.
It's actually worse than that.
Really?
Yeah, it's not just the journey through the solid that's difficult, it's the connection points. A liquid naturally soaks into all the microscopic, porous nooks and crannies of the electrodes. It makes perfect contact.
Because it's fluid.
Exactly. But if you take two solid materials, the new solid electrolyte and the solid electrode, and you just press them together, they don't mesh perfectly.
Okay.
If you zoom in on a microscopic level, it looks like two mountain ranges being pushed together. They only touch at their absolute highest peaks.
Leaving all the microscopic valleys between those peaks as empty air gaps.
Yep.
And ions can't jump across empty air, so you get massive electrical resistance. The battery just doesn't work.
Historically, the only way laboratories could overcome that mountain range problem was by putting the test batteries under extreme external pressure.
How extreme?
They would apply 10 megapascals or more, just to literally crush the solid materials together until they deformed enough to touch.
Okay, I looked up what 10 megapascals actually translates to in the real world. Just to put that in perspective for you listening, that's like parking two heavy Ford F-150 pickup trucks directly on top of your smartphone just to force the materials inside the battery to make contact.
It's an absurd amount of force.
Obviously, you can't install a giant hydraulic press inside a commercial cell phone or a sleek car chassis.
Which is why solid state was stuck in the lab for so long. But this is exactly where the 2025 breakthroughs completely changed the game.
Yes, let's get into the breakthroughs.
The Institute of Physics, under the Chinese Academy of Sciences, published a paper that fundamentally solved the sandbox problem.
The iodine-ion doping technology.
That's the one.
Let's break down how this actually works because, doping sounds like sports cheating. But in chemistry, it's actually a structural hack, right?
Yeah. In material science, doping means intentionally introducing impurities into a crystal to change its properties. Okay. So imagine you have a dense, solid brick wall representing the solid electrolyte. The lithium ions are trying to get through it, but they keep crashing into the bricks.
Right.
What the researchers did was swap out some of those solid bricks, for hollow ones in this case, by introducing iodine ions into the material's crystal lattice.
So they essentially paved a smooth, microscopic tunnel system right through the solid material.
That's the brilliance of it. By altering the molecular structure, they drastically increased the inherent permeability of the solid. The lithium ions could suddenly trek through the material freely.
Wow.
They completely eliminated the need for that massive external hydraulic pressure. The technology finally worked in a practical, real-world form factor without needing 2 pickup trucks of weight on top of it.
That is a massive leap forward. But as our sources from Bloomberg NEF point out, proving the physics in a lab doesn't automatically put the battery in your driveway.
No, definitely not.
There was a secondary, equally massive hurdle, which was the manufacturing cost. Switching from making liquid batteries to solid batteries isn't just a simple software update on the assembly line.
One of the industry reports framed it perfectly, actually. It's not like a factory upgrading from an iPhone 14 to an iPhone 15. It's like a factory that makes perfectly good bicycles suddenly deciding to build motorcycles.
Right.
They both have 2 wheels, but absolutely none of your tools, parts, welding techniques, or safety protocols apply. You have to scrap the entire factory and start over.
The sources compared it to switching from making steamed buns to baking bread. You have to buy all new equipment. And the specific villain here was the sulfide material they were using for the solid electrolyte.
Yes, sulfides are highly conductive, which is great for batteries, but they are incredibly finicky. They are hypersensitive to ambient moisture.
How sensitive are we talking?
If a single drop of humidity in the air hits a sulfide electrolyte during manufacturing, it chemically reacts and off-gases highly toxic hydrogen sulfide.
So to build these batteries, companies were having to construct these hyper-expensive dry rooms.
Huge ones.
We're talking massive, multi-billion-dollar clean rooms that are mathematically drier than the Sahara Desert, just to ensure the factory didn't accidentally gas its own workers.
The capital expenditure was astronomical. But then, right at the start of this year, 2026, the University of Science and Technology of China dropped a genuine bombshell in the industry.
This is the zirconium breakthrough.
Exactly. They moved away from sulfides entirely and developed a brand new solid electrolyte using zirconium tetrachloride as the core raw material.
The numbers on the zirconium breakthrough are staggering. First off, it costs just 1/20th of the mainstream sulfide materials.
A massive cost reduction.
Second, it is 10 times harder than traditional oxide materials, meaning it acts like an absolute fortress against any of those needle-like dendrites trying to pierce through.
And most importantly for the business side, it is remarkably stable. It doesn't violently react with moisture. You don't need the billion-dollar dry rooms. Because of this stability, many of the existing traditional liquid battery assembly machines can actually be repurposed to manufacture it.
Okay, let me stop you right there because this is where the timeline gets confusing for me.
Okay.
If this zirconium tech solves the physics and it bypasses the multi-billion-dollar manufacturing equipment problem and it works on repurposed machines, why is my driveway still empty?
Well,
Why do the industry roadmaps in our sources universally state we have to wait until 2030 for mass affordability? What is stopping a company from pumping these out tomorrow morning?
because repurposing an assembly line and mastering the scale of production are 2 entirely different beasts. We have officially entered what automotive engineers affectionately call production hell.
Production hell.
You have to understand the difference between a laboratory B sample and mass manufacturing.
A B sample being like a fully functional prototype that proves the chemistry works.
Right. QuantumScape, for example, shipped their QSE5 B samples to automotive partners recently. They work perfectly. But building one flawless battery cell in a controlled lab, or even 1,000 cells in a pilot facility, is child's play compared to producing millions of identical flawless cells every single week.
Because the margins for error are so small.
Exactly. If your manufacturing tolerance is off by a fraction of a millimeter on a liquid battery, The liquid kind of shifts and accommodates it. If you are off by a fraction of a millimeter on a solid-state cell.
You get those microscopic mountain ranges again?
Yep.
The air gaps return, the resistance spikes, and the cell is basically useless.
Exactly. The precision required at scale is unprecedented, and that drives up the current cost disparity to an eye-watering degree.
Yeah, Bloomberg NEF reported that by 2025, traditional liquid lithium-ion battery costs had fallen to around $115 per kilowatt hour.
While solid-state manufacturing costs were sitting anywhere from $400 to $800 per kilowatt hour.
That's a 5 to 10 times price premium. To put that in perspective, if a standard EV battery pack costs $10,000 today, a solid-state version would cost between $40,000 and $80,000.
Yeah, you obviously cannot put an $80,000 battery into a Honda Civic.
No one would buy it.
Furthermore, you have the automotive validation cycle. You don't just invent a new chemical architecture and throw it onto the highway at 75 miles an hour. These B samples have to endure brutal, real-world torture testing.
The sources outline this testing, and it sounds like a literal gauntlet. We're talking about taking the batteries and freezing them solid at minus 40 degrees Celsius, then baking them in ovens at 85 degrees Celsius.
They subject them to violent, high-G crash impacts to ensure they don't shatter internally.
They run them through thousands of extreme fast-charging cycles to ensure the solid material doesn't degrade over time. That validation takes years, not months.
Which brings us to the actual commercial rollout roadmap we are looking at today. Based on the consensus across MDPI journals, Bloomberg, and the automakers themselves, 2026 is officially designated as the inaugural year of verification.
Meaning small batches.
Right. This is the year automakers putting these cells into small, tightly controlled fleets of test vehicles on closed tracks.
And then 2027 to 2028 is when the dam starts to break. Toyota has explicitly targeted 2027 to 2028 for their initial commercial rollout. Samsung SDI is also aggressively targeting mass production in 2027 for their high-end anode-less solid-state cells.
But again, because of that massive cost premium we discussed, those 2027 vehicles are not going to be standard commuter cars.
No.
They're going to be ultra-premium luxury models, likely flagship vehicles under the Lexus brand, or high-end performance sports cars where the buyer doesn't mind paying a $20,000 premium for cutting-edge tech.
It's the classic trickle-down technology model. It'll take another 2 to 3 years of those luxury sales funding the supply chain to squeeze the manufacturing costs down. The projections show that by 2030, the cost of solid-state will drop closer to parity with liquid batteries, around 0.8 to 1 yuan per watt-hour.
2030 is the inflection point. That is the moment the floodgates open for large-scale, affordable, commercial application across all vehicle classes.
So 2027 for the wealthy early adopters and roughly 2030 for the rest of us.
Right.
But here's where it gets really interesting. What will this technology actually feel like to use? Like, when this finally hits your driveway or goes into your pocket, how does it physically change your day-to-day life?
It represents a total paradigm shift in consumer expectations. Let's look at the baseline metric energy density. Currently, those volatile liquid lithium-ion batteries sit somewhere between 150 and 300 watt-hours per kilogram.
Okay.
Solid-state technology pushes that density up to between 300 and 900 watt-hours per kilogram.
Meaning you can essentially double the range of a vehicle without adding a single pound of weight to the chassis.
Yes.
Or, conversely, you could cut the physical size and weight of the battery pack in half, keep the exact same range you have today, and make the car massively more efficient, nimble, and just cheaper to produce.
Practically speaking, for the average driver, it means easily breaking the 1,000-kilometer range barrier on a single charge.
That's over 620 miles. You could drive from Los Angeles to Salt Lake City or from London to Zurich without stopping for power once.
It's incredible.
And when you finally do need to stop and plug in,
The charging speeds are revolutionary. Remember earlier when we talked about the thermal runaway risk of liquid batteries?
800-degree jet flame.
Exactly. Because the new solid electrolyte doesn't have that highly flammable liquid, it doesn't run the risk of boiling and catching fire when exposed to massive amounts of electrical current. You can safely pump electricity into it at a staggering rate.
Which is how QuantumScape's verified B samples have already demonstrated charging from 10% to 80% capacity in just 12.2 minutes.
12.2 minutes. Think about that.
That completely changes the psychology of a road trip. That's barely enough time to grab a coffee, stretch your legs, and use the restroom. You plug in, walk inside, walk out, and you have another 500 miles of range ready to go.
And we also have to talk about environmental resilience. If you live in a cold climate and you've ever watched your EV's range inexplicably plummet by 30% just because it snowed outside, You know the exact frustration we're talking about.
Oh yeah, winter range anxiety is real.
The liquid inside traditional batteries literally thickens and becomes sluggish in freezing temperatures.
But solid state effectively solves that. Because there is no liquid to freeze or turn to slush, the winter range degradation can be controlled to within just 10%.
It's a game changer for colder regions.
Furthermore, because the solid zirconium physically blocks those dendrite spheres from growing and chewing up the battery's internals, the overall lifespan skyrockets. We are looking at lifespans of 10,000 to 100,000 charge cycles.
Your battery will, without a doubt, physically outlast the car it is installed in. It outlasts the phone, the laptop, the smartwatch. And this brings up a crucial point from our sources. This revolution isn't just about the automotive sector.
Right. We spend so much time talking about cars, but the medical applications here are genuinely life-changing. Imagine a cardiac pacemaker powered by a solid-state battery. You have zero risk of a toxic organic solvent leaking into a patient's bloodstream. You have zero risk of the battery swelling and causing internal damage.
And because of that 100,000 charge cycle lifespan, the patient never has to undergo a secondary surgery just to replace a dead battery.
The broader implications for consumer electronics, aerospace, and medical fields are profound. You are fundamentally removing the risk profile from portable power.
But returning to the automotive market for a moment, because that's where the billions of dollars of R&D are currently flowing, this kind of performance reshuffles the entire industry deck overnight.
Which really makes me wonder about the current market strategies. If an EV can drive 1,000 kilometers, charge in 12 minutes, and barely lose range in a blizzard, doesn't that instantly make plug-in hybrids and extended-range EVs entirely obsolete?
It really does.
The whole selling point of a hybrid is that the gas engine is a safety net for your range anxiety.
Yeah.
But if the anxiety is completely cured by solid-state tech, that safety net just becomes dead weight.
That is the exact existential crisis facing legacy automakers right now. The Gasgoo analysis specifically notes that the best of both worlds value proposition of hybrids is going to lose its luster very rapidly.
Why would a consumer choose to carry around a heavy internal combustion engine, a complex exhaust system, a catalytic converter, and a tank of flammable gasoline requiring constant oil changes and maintenance if their solid-state battery can do everything perfectly on its own?
They wouldn't. Whoever secures this solid-state technology first and proves they can manufacture it at scale essentially writes their own ticket for the next decade as the auto industry.
It is a brutal winner-takes-all technological race.
It is. Traditional automakers who lack the funding or the supply chain integration to secure these solid-state partnerships are going to find themselves pushed into the third tier of the market within 5 years.
Wow. Okay, let's take a breath and recap the journey we've just been on.
Sounds good?
We started by exploring the terrifying reality of the chemical cauldron in your pocket and the electrochemical ceiling that limits our current liquid batteries.
Yeah.
We broke down the massive 2025 and 2026 physics breakthroughs, iodine doping to create microscopic tunnels through the solid sandbox, and low-cost zirconium electrolytes that finally eliminate the need for billion-dollar dry rooms.
Huge milestones.
We confronted the gritty reality of production hell and the 2027 to 2030 commercial timeline. And finally, we looked at the incredible 1,000-kilometer, 12-minute charging reality waiting for us at the finish line.
It is an incredible roadmap. But before we wrap up today's Ink Dive, there's one final, incredibly provocative concept from our research that we need to debate.
Oh, I like the sound of that. Lay it on us.
We've spent this entire time talking about pure solid-state batteries as the ultimate inevitable destination.
You're right.
But while the industry is waiting for pure solid-state to escape production hell and reach cost parity in 2030, they aren't just sitting still. There is a highly effective bridge technology being deployed right now called the semi-solid or quasi-solid battery.
Wait, if it's semi-solid, that means it still has liquid in it. Doesn't that mean it still carries the thermal runaway fire risk we've been trying to escape this whole time?
It's a compromise, but a brilliant one. Remember the two mountain ranges touching problem?
The microscopic empty valleys that cause massive resistance.
Right. Instead of engineering a perfect pure solid interface, semi-solid batteries use mostly solid materials, but they introduce just a tiny, tiny fraction of liquid or gel polymer to wet the surfaces.
Like a lubricant.
Exactly. It acts like a drop of oil between two gears. It perfectly fills in those microscopic valleys, ensuring flawless electrical contact without needing a 10 megapascal hydraulic press.
Okay, so it drastically simplifies the manufacturing process. But what about the fire risk?
Because the volume of liquid is so incredibly small compared to a traditional battery, the flammability risk is exponentially lower. It's not a sloshing liquid highway. It's just a damp road.
Ah, I see.
You get 80% of the safety benefits of a pure solid-state battery and a massive bump in energy density, but you can build them cheaply using today's existing factories. In fact, they are already out of the lab and in the wild.
Really?
Yeah, they are currently powering the $15,000 MG4 electric car, and they are actively being used in a massive 200-megawatt grid storage facility in Inner Mongolia right now.
So the technology has already proven it's cheap and it's on the market today.
Yes. So the provocative thought I want to leave you with is this traditional liquid lithium-ion battery prices are plummeting. They recently hit that $115 per kilowatt hour mark.
Right?
As liquid batteries get dirt cheap, and these semi-solid bridge batteries provide a massive safety and performance boost without requiring a complete reinvention of the global supply chain, will pure 100% solid state ever actually take over the mass market?
Now, that is a fascinating question. Is the holy grail of pure, flawless, solid-state physics actually necessary if the semi-solid compromise is good enough and radically cheaper to produce? It really makes you wonder how the brutal realities of economics will eventually dictate the limits of our material science.
It's the ultimate battle between engineering perfection and commercial pragmatism. And the winner will power the next century of human progress.
I absolutely love that. Thank you all for joining us on this deep dive. Keep questioning the technology that powers your world. And the next time you look at the battery percentage on your phone or your dashboard, remember that volatile, sloshing liquid highway inside your device, it's finally about to get paved over.